let's continue the first chapter with the voids. So what are voids? Even though all the atoms are closely packed in a unit cell, but there are empty spaces that are that occurs in between the atoms. So these empty spaces are known as voids, or sometimes called as the interstitial voids. Now, depending on the charge of the species, the entity, if it's a cation, then it tends to be smaller because of the lesser amount of negative or electron cloud over it, and then the cations are bigger because of the larger electron cloud over it. So we'll try to understand the types of voids or the empty spaces in between the atoms. So let's start with the two-dimensional voids. So if we look at this arrangement, this figure, so there are three atoms surrounding the smaller atom at the center, and that space is what we call the void or the empty space. Now we can think about these bigger atoms as the cations and the smaller one inside the cavity or inside the space, empty spaces. We can consider it to be the anion. Now we can calculate the radius ratio in between these two atoms or entity. So let's try to extrapolate the structure. So I've extrapolated the structure, the figure. I've drawn an equilateral triangle from the center of each of the atoms, and I've extrapolated another smaller triangle which I've drawn here, taking the center of the smaller atom. Now if we take out only the smaller triangle, it should look like this. The bigger radius we denote with the big R, the capital R, and the smaller one we denote with the small r, the smaller radius. Now if we take all this into account, then the side of this will be the big R plus the small r, and then if this is an equilateral, it should be an equilateral because all the sides will be equal, so it'd be 60 degree. And if we make it into half, or if we extrapolate in the middle, then we're getting 30 degrees. Now since we have the hypotenuse and the adjacent to the angle inside the triangle, so it would be cos theta or cos 30 degrees for finding the opposite. So cos 30 will be equal to cos 30 cos adjacent over hypotenuse. That will give us the, so if we again cos 30 shift it, then it should be r plus r over big R. Now if you divide this with the value of cos 30, then you should get around, the value would be around 1.155, and so this would be 1 plus r over r. So the radius ratio r over r would be 0.155. So that is our radius ratio in two-dimensional voids. So let's try to solve for a three-dimensional or a tetrahedral void. So for a three-dimensional void, there are two types. One is tetrahedral and the other one is octahedral. Now in tetrahedral void, it is similar to that two-dimensional void where we have 3 atoms at the base, and on top of this we have another atom. We have another atom creating a tetrahedral void. The cavity or the space between them will be the shape of a tetrahedral, if you imagine. So, and like we've discussed, there will be a smaller cation inside that cavity. So to calculate this, let's extrapolate again. So if we extrapolate the structure, if we draw the triangle inside, so we'll get something like this: r plus r. That means if we take the radius of the bigger atom to be capital R and the cation to be the small r, then we'll get something like this. And we know that the angle in a tetrahedron, the angle is around 108.88. So if we split it into 2, then we get around 54.44, 54 degrees 44 prime. So, and then we have the hypotenuse and the opposite. So hypotenuse, so sine theta, or sine, if we split sine 54, then it's opposite over hypotenuse. So katoa, r plus r. Now if you plug in the values, then our ratio would be, for a tetrahedral void, will be 0.225. Now you can check for octahedral void. The calculation, the radius ratio comes to be around 0.414, and then for cubical void, the radius ratio is around 732. So those are some of the values which you need to remember. So here's a question. Okay, now I've adjusted. So copper has a face-centered cubic structure, and they've given us the edge length of 3.61 angstrom, and they are asking us what is the size of the largest atom, that means this one, which could fit into the interstices, the empty space of the copper lattice, without distorting it, without disturbing the structure. So we know that the relationship, the radius ratio is r by, for octahedral, it's 0.414. So our octahedral would be 0.414 r, and the relationship between the big R and the site is for FCC, it's 4R is equal to root 2a. If you have calculated the packing efficiency for FCC, you would have found this relation. So our R would be nothing but root 2 over 4a. So now we just plug in the values. We have collected all the values. So small r is equal to 0.414 into this r. So we'll just plug in the values. 2 into a is given as 3.61 angstrom over 4. So our answer for this radius would be 0.53 angstrom. Now with the same analogy, you can even calculate the radius ratio for the relationship between the cation and the anion type. So you can go through that. I think I've provided you in the readout. Now let's move on to crystal defects and properties of solids. So even though the crystals are packed, uh, they have defects or imperfections within it. There are some the imperfections or the defects can be due to conditions under which the crystals have been developed or impurities. Even temperature affects the crystal formation or the structure of the crystals, and some of the imperfections can be point defects, line defects, plane defects. Now point defects can be stoichiometric or non-stoichiometric. Now in stoichiometric defects we have the Schottky, Frankel, and the interstitial voids. Now let's look at one of the other the stoichiometric defects. So let's picture the arrangement of the cations and anions in this form. If we take these the bigger dots or the bigger dots to be anions and the smaller ones to be cations. Now, so if 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 there are points missing, like both the ions missing from different areas, then those are called as the Schottky defect. SCHO Schottky defects, and it will those missing points will be equal. That's why it's called the stoichiometric. It will be in stoichiometric amounts. The missing ions will be in stoichiometric amounts. That means equal amounts, even amounts. And then for another of these stoichiometric defect is the Frankel defect. But in Frankel defect, we'll have only some of the cations, or in some other arrangement, the cations will be missing in equal amounts, or maybe in some other arrangement the anions will be missing in equal amounts. So that's the Frankel defect, the Schottky and the Frankel defect. That's the difference. And when we talk about interstitial defects, some in between the voids, again there will be some other impurities which will be present. So those defects created by those impurities are called as the interstitial defects. And in non-stoichiometric defects we have the metal excess or cation excess defects, or sometimes or the other one would be metal deficiency or the cation deficiency defects. So those comes under non-stoichiometric defects. Now let's move on to some of the properties of solids. So there are lots, but the two or the most common ones are the electrical properties and the magnetic properties. So we know what are electrical and magnetic properties. So depending on the conductivity or oh yeah, depending on the conductivity of that particular metal, they can be classified as good or bad conductors, or whether they can conduct electricity, electrical property, or whether they show electrical properties or not. They can be classified as insulators also if they don't, or semiconductors for that matter. So let's discuss one after the other. So these are the differences between conductors, insulators, and semiconductors. Now, how does metals conduct electricity, or they have electrical properties? Now, there are two bands, the valence band and the conduction band. Once the electron from the valence band, now here we have, in the valence band we have lots of electrons. Now, once this enters into the conduction band, then the electricity, or that particular metal can conduct electricity. In conductors, the energy difference between this conduction band and the valence band is negligible, or in fact they seem to be merged. So the valence electrons can easily enter into the conduction band, and then or they can conduct electricity through those electrons. But in case of insulators, the energy gap between the valence band and the conduction band is too big. So the valence electrons, or the electrons in the valence band, cannot jump into the conduction band. Therefore, they don't pass electricity. In case of semiconductors, the energy gap between the conduction band and the valence band is small. So how will it conduct electricity? So if we can somehow close this gap between the valence band and the conduction band, then they show electrical conductivity. Hence they're called the semiconductors. So we'll discuss further on that, semiconductors. So how does semiconductor conduct electricity, or becomes conducting? So what we do is we call doping, or introducing impurities into the semiconductors. Like suppose silicon and germanium, they are considered as semiconductors because only on their own they don't conduct electricity. But if we dope, or if we add atoms such as phosphorus or boron to them, then they start conducting electricity. Suppose in case of silicon, we know that 3s2 3p2 is the electronic configuration of silicon. So if we dope silicon, or if we add phosphorus in silicon, suppose 3s2 3p3, now there is a difference in the number of electrons in between silicon and phosphorus. Now phosphorus has one electron more than silicon, so because of that extra electron, the the gradient, the electron gradient, the differences in the electron gradient makes this extra electron is responsible for carrying or conducting the electricity. And when you dope silicon or germanium with phosphorus, since the conduction is done through that extra electron, so it seems it's like the negative charges are carrying the charges. Therefore it's called n-type semiconductor. N-type semiconductor. But if we dope this silicon with a boron, 2s2 2p1, so here in boron, the boron is short of one electron. So because of that deficiency, again, electron from this silicon may enter into the orbital of this boron, and then they'll conduct electricity. So it seems the charge carrier are the positive charges, so they are called p-type semiconductors. That's the difference between n-type and p-type semiconductors, and how semiconductors can also conduct electricity. And then we have the other property of solid is our magnetic properties. I think Like the magnetic properties includes ferromagnetism, diamagnetism, antiferromagnetism, and so on. So I suggest you go through those magnetism or magnetic properties, how they are generated, how the magnetic properties come into being. So we'll try to solve one or two examples and then wrap up with this chapter. So here's an example. Titanium, the density of titanium is given, edge length is given, and then they're asking at what cubic unit cell does titanium crystallizes. So we know the the mass of titanium, it's 48 units, so we know that that density is nothing but z into the mass over a cube and Avogadro's number and not. So 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 they have given us the density, we know the edge length they have given, Avogadro's number 6.022 in the 10 raised to the power 23, and the mass of titanium is given. So by knowing the contributions per atom, we can know in what cubic unit cell titanium crystallizes. So if you plug in the values, you'll get the value of Z around 4. So 4 is body standard cubic system. Try to solve on your own. So here is another question. Sodium metal crystallizes in body standard cubic system, and they've given us the edge length. They're asking us the radius of sodium atom. Now we know that the body diagonal for BCC, body center cubic center, it's 4r is equal to root over 3a. So plug in those values and we'll get the radius. Root 3 into a is given as 4.29 angstrom over 4. So the radius of sodium atom, you'll get around 1.86 angstrom. So that's how we can calculate different examples. Now I'll give you one or two examples. You try to solve on your own. You have my number if you want any help, so you can contact me. So here are some more questions, so you can try, and if you have difficulty, you're gonna contact me. So let's wrap up the first chapter with this.